Hey kids, this is Mrs. Mooney, and this video is about transformations of function graphs. Now we can take any function and we can translate it left or right or up or down. We could stretch it, we could compress it, we could do that horizontally or vertically. We can also do reflections across the x-axis and the y-axis. And so the general format that we're going to use for any transformed function is going to look just like this. You've got the f of x equals, and then you'll have a positive or a negative and then an a, and then you'll have the function. So f of right here just means the function, whether that's x squared, x cubed, or whatever other function we learn about this year. And then we've got another plus or minus b, so there's another number that could go in there, multiplied by x within the function. We can subtract within the function or add, and we can add or subtract after the function. So we'll start with just the translations. When I take a value k, so this last value here, and I add it to a function, then I'm going to translate the function vertically. So this k right here is always your vertical translation. When I have a value h and I subtract it from x, then that's my horizontal translation. So if I subtracted 2, I'd be going right 2. If I added 2, then I'd be going left 2. If I subtracted 2 at the end of the function, after the function, then I'd be going down 2, and if I added 2, I'd be going up. So the vertical goes the direction of the sign that you think it is, but the horizontal goes the opposite direction from the sign, and that's why we have a minus in our main function, because it's there to tell you go the opposite. So here's an example. First we'll go with just vertical, and I want you to consider this generic function, so just sketch this into your notes. Now if we add a k value of 4 to this function, then we're changing it by adding 4 to each y value, because if I just said f of x plus 4, well, that's just like saying y plus 4. So I'm going to take all the y values that I had in my chart and I'm going to add 4. Okay? So every y value you had before is now up 4 from where it was. Or say we added a k value of -3 to the function, so we had f of x minus 3, or I guess I have it written right here. Then that just means that I'm taking each y value and taking away 3. So I would have all of these y values, subtract 3 from them, those are your new y values. Basically, like I said, it's taking the entire function and shifting it down 3 units. So as I said, your translated graphs would be, for the plus 4, we'd be shifted up 4, it would look just like that. And for the minus 3, it would be shifted down 3. It would look just like that. Alright, now I'm going to take the same example, the same parent graph, so the original one that you drew, and we're going to do a horizontal example. So now we're going to mess with the h value. So we're going to let h be 2. That means we're going to graph f of parentheses x minus 2. That means I'm going to subtract 2 from the x, and then plug it in and get what y I'm looking for. Another way of saying that is each x value that we choose has the y value of what used to be 2 units before it. Or an easier way of saying that, even easier, is the graph is shifted 2 units to the right. So just keep in mind this minus 2 means we have to compensate by shifting the graph the opposite direction. So minus 2 would take it 2 units to the right. So remember, like I have in here, it's the opposite of the sign because we're subtracting it from the x. And then if h is a negative number, if I said let h be -3, then I'd have x minus -3. That's where we have x plus 3. And so a negative goes to the, -3 shifts it to the left. Alright, now here comes the harder part, the stretches and compressions. If you multiply by a parameter outside of the function, it will stretch or compress the graph vertically. If I take my y values and multiply them by something, if I multiply my height by 2, then it doubles. If I multiply my height by 1/2, then it compresses. If you multiply by a parameter inside the function, so you're multiplying just the x, not the whole function, so not y, but x, then it will stretch or compress horizontally. So here I've taken the same example that we started with, and now I've got 2f of x. So I'm multiplying on the outside, and I'm multiplying each y value by 2. So if I look in my chart, I've doubled each y value. And so when we plot that, the pink is the graph here. And if you look, it's not shifted up 2. It's the positives are higher by 2, but the negatives are lower by 2. So the whole thing has become stretched vertically by a factor of 2. Basically, it's twice as tall as it was before. Now we could take the same example and instead we'll let a be 1/2. So if we're multiplying by something that is less than 1, then we're going to be compressing it. Just like, you think about that. If I multiply something by a number less than 1, the answer will be smaller. So if I took all my y values and I halved them, then each, like half of 2 is 1 and half of -2 is -1. The whole graph is now half as tall. So we say compressed vertically by a factor of 2. Sometimes you might see someone say compressed by a factor of 1/2. Just know if they use the word compress and half in the same sentence, they're still using their a value as 1/2. They're just thinking about, okay, a is 1/2. So it's compressed vertically by 1/2. You could say by a factor of 2 or by 1/2. Either one makes sense. And then the horizontal works opposite from the vertical. So if I let b be 1/2, that means I'm multiplying just the x inside of the function by a 1/2. That means that each x that we are choosing gets the y value of what half of that x value had in the original function. It's kind of confusing, but an easier way of saying this is we're going to stretch it horizontally by a factor of 2. So it's the reciprocal of this, the reciprocal. If I have 1/2 x, I'm actually getting wider by a factor of 2, so we say stretched horizontally. And if b is between 0 and 1, like I said, you'll have a stretch, so it's the opposite of what the vertical did. The vertical, if it was between 0 and 1, it compressed it. And if b is greater than 1, then you'll have a horizontal compression. So it's the opposite. Just keep that in mind. Just like the left and right shifts are opposite for x and y as they are for, they're opposite for x as they are for y. Okay, something else that's very important that you need to know, that you need to note the difference between f of parenthesis b parenthesis x minus h, close, close, and g of x, which would be f of parenthesis bx minus h. Basically, this one has an extra set of parentheses right here. This is the proper form, okay? If you see it in this form, the b must be factored out first in order to get the correct value for the horizontal shift. Here, let me do an example. Alright, so if I took g of x is f of, and then parentheses 2x minus 8, it looks like we're saying, okay, 2 times the x, so we're compressing by 2, it's going to be half as wide, and minus 8, so we're shifting right 8. However, that 2 has to be factored out first. So if you factor out the 2, then in the parentheses you have x minus 4. The 4 is actually your shift. You'll be shifting right 4, not 8. Make sure you keep that in mind because we will throw some at you where they're factored and some where they're not. And you've got to remember that they have to be factored before you can decide what your horizontal shift is going to be. Alright, and then the easiest of the transformations is the reflections. If I have a negative out in front of my function, if the a is negative, that's going to reflect the graph across the x-axis. So all of my positive 2 now becomes negative 2, or vice versa here. My positive 2 becomes negative 2. My negative 2 becomes positive 2. So the whole thing flips over. But don't tell me it flips over. Tell me it reflects across the x-axis. Now if b is negative, if it's negative inside the function, so only the x is negative, not the whole function, that's going to reflect the graph across the y-axis. So positive 1 becomes negative 1. Positive 3 here becomes negative 3. Positive 5 here becomes negative 5. So it reflects it across the y-axis. So you can't say flip here either because I don't know which one you're talking about. You've got to say reflect across the y-axis. Now the last thing that we're going to do in this video is modeling, and we're going to use a quadratic as an example. So here's a word problem for you. We've got the netting of an empty hammock. It hangs between its supports along a curve that can be modeled by a parabola. So if you see in the background there's a hammock on supports. Here's the hammock right here, We're going to use a parabola to model the shape of it. Parabolas are quadratic. We'll get more into quadratics in another chapter, but right now you know that x squared makes a parabola. In here, the unit of measurement for both axes is feet, so they've put a coordinate plane right there. They just chose to put it there, and so this point is at 3, 3, and this point is at negative 2, 4, and this point is at 8, 4. And it says, find a quadratic function that models the hammock's netting and state the function's domain. So as I said, the parent function is going to be x squared. F of x equals x squared. And then we have to find the parameters that change it, because y equals x squared is 0, 0, 1, 1, 2, 4, and it's a parabola like that. But that's not what this is. It's been stretched out, we can tell, or compressed vertically, stretched horizontally, one or the other, or both really. And it's been moved to the right and up. So let's figure out what these parameters are. Alright, so if I took my function f of x is x squared, then f of x with our changes, we could have a positive or a negative, we could have an a value, and then positive and negative and a b value, and then we can have a horizontal shift, and then we have the squared, because that's the only thing that's in the function, and then after the function, we could have plus k. And then here it says, because it is squared, the b value can be combined with a and left out. And that's like I was saying, well, is that horizontally stretched or is it vertically compressed? It's either one or both. Our a and our b can be in either place because it's a squared model. So we're just going to leave the b out of this altogether. We're going to call it an a value. So that cleans it up a little bit. We took out the b. And then I know that my parent function has a vertex at 0, 0. So anytime I shift a parabola, I know that wherever my vertex goes, we have a horizontal shift h and a vertical shift k. I can look here and go, well, my original vertex would have been there. I went to the right 3, and I went up 3. So that tells us the values of h and k. We went right 3, so we know we're going to do x minus 3. And we went up 3, so then after the function we'll have a plus 3. So now the trick to finding the actual equation of this is to take our parent, take what we know it looks like with letters, and then we're going to take another point, and you can use either this one or this one. It does not matter at all. I'm going to go with this one because that has negative, and negatives are ugly, right? And we're going to plug that in as x and y. Remember, f of x is the same thing as our y. So we're going to have, our y value is 4. And then I don't know what a is yet, so I'm going to leave it as the letter a. And then that's my x, right there, 8 minus, and then we already figured out h and k. H was 3 and k was 3, so 8 minus 3 squared plus 3. So now the only variable left in this problem is a. So what you do is you figure out h and k, you figure out one other point on the parabola and put it in for x and y, and then that just leaves you with a to solve for, and that's easy to do. So here I have it typed out so you can actually read it. When we take away, we just take away 3, we square the 8 minus 3 is 5, squared is 25, and then divide by 25, and here we go, a is 1 over 25. So then when you know a, you just go back, rewrite the equation. F of x equals, we have our a here. I didn't mean to move that, sorry. There we go, I was looking for this. We have our a here, x minus h here, squared, and then plus k here. And then we have to think, this is a real-world situation. This is a word problem, so you've got to think logically. This is a hammock, and so we have to restrict the domain. The endpoints of the hammock are here and here. So the domain, and this confused me before because I was like, no, they're not. They're over there and over there. I guess they're assuming that this is rope. Okay, so this is the hammock part right here and right here. So the domain of the hammock itself, only the hammock, would be from this x value, -2, to this x value, 8. And so we would say in set notation, x given -2 is less than or equal to x is less than or equal to 8, or in interval notation, which I prefer, hard bracket -2, comma, hard bracket 8. And then, of course, restricting your domain automatically restricts your range. So you don't have to talk about the range when you're doing your real-world problem. You just restrict your domain, and then it's all taken care of. And because this was another long, boring video, I'm going to leave you with a joke so you can end on a laugh. And I'll see you guys tomorrow. Have a great night.